today with us, we have Yann LeCun. Yann is a French-born computer scientist, often described as one of the godfathers of AI and deep learning. He's chief AI scientist at Facebook. He's professor at the NYU Center for Data Science and the Kieron Institute of Mathematical Science. And he's the winner of the 2018 Turing Award, also known as the Nobel Prize of Computer Science. Welcome, Yann. Really glad to have you on the podcast here.
Really glad to be here with you.
So, as we're talking about connecting with people, I'm kind of thinking back to what I thought, for me at least, was a pretty pivotal moment in the AI world. We talked about 2012, the ImageNet moment, but then soon thereafter, 2013, I remember it's NeurIPS, again, the big conference we all go to, and we go there to nerd out. We talk about equations, programs we write, ideas that I would say until then, pretty much nobody cared about, except for the maybe few thousand of us showing up at that conference. But in 2013, there's this rumor, and it's like, oh, Mark Zuckerberg is at the conference, founder, CEO of Facebook. And it's like, wait, what is this? What is founder, CEO of Facebook doing at this conference? He's not a machine learning researcher. This is machine learning researchers here. And then I see him on the schedule. He's on the schedule for the deep learning workshop, Q&A with Mark Zuckerberg, it says. One of the next days, it was 2 days later. And then I hear, apparently he's already here. And last night he was hanging out with Yann LeCun and a few other people. And I'm just like, what's going on here? And obviously you were hanging out with him, and I'm kind of curious. You must not have met him the first time at the conference. There must have been some buildup towards that. And what was that whole transition from deep learning, first of all, being largely ignored, then in 2012 being widely accepted as the promising path forward, and everybody's starting to work on it after you worked on it for so long. All of a sudden, everybody's following your path, not just you, but you and several others, of course. But then all of a sudden, industry gets interested. How did you experience that? Industry gets interested in transition.
So funnily enough, there are a few companies that actually were interested in deep learning and convolutional nets before 2012. One of them in particular was NEC, where I worked briefly in 2002, 2003. And I worked on things like phase detection, pedestrian detection, things like this. And after I left, another person kind of joined called Caillou, who basically picked up on a lot of those projects and sort of became a big fan of those convolutional nets. And he got NEC to actually commercialize some products that were based on convolutional nets, like vending machines in Japan that would like recognize your age and gender, so they could, so this was in the.
I would say that's flown under the radar largely. I don't think.
Yeah, no, that was like pretty much under the radar. That happened around 2000, like the commercialization of those things around 2010, 11 or so. But they've been working on this like for longer. There was even a spin-off of NEC that built like surveillance, like video surveillance systems based on pedestrian, person detection using convolutional nets. But I was disconnected from this afterwards. But what happened in 2012 with the ImageNet competition is that it attracted the attention of a lot of people, engineers in industry, and there was a particular group of engineers at Facebook who was working on computer vision. And it was mostly exploratory because they didn't know what they could use computer vision for really at Facebook. But they started experimenting with convolutional nets, and we're getting really good results for things like, classifying images, figuring out if there were like, offensive material or not, or doing face recognition, stuff like that. And Mark was really impressed by the results. And at the same time, he was going through kind of a thought, this was a relatively short time after Facebook, became a publicly traded company, and it was turning 10 years old pretty soon, and Google Plus was on the way out, so they were not like fighting for their survival anymore. They were basically very well established in the social network thing. So Mark and Schrep, Mark Schrepfer, the CTO, were thinking about the next 10 years, like what are going to be the big challenges for us over the next 10 years? And AI sort of came on top. Basically, that was like, it was going to be a key technology for, getting Facebook to move forward.
So what happened? Did they just cold email you, or?
Yeah, so I met some of those guys working on this at CVPR, and then I got a video call with Schrep, the CTO of the company. He wanted to kind of know, first of all, actually with the manager of that group, Srinivas, and then with Schrep in the summer, roughly, of 2013. We wanted to kind of get the lay of the land, like what are the cool things, and what are the things we should be watching, looking for, how do we get into that field, like who should we hire, stuff like that, right?
I think they're really looking for advice more at the time.
Yeah, it was more advice. That's right. And then I had a call with Mark Zuckerberg. This was maybe before that. I get an email or call from a former student of mine who was working at Google at the time, Mark Aurelio Ronzato, whom you know, and he tells me, I'm being recruited by Facebook. And I tell him, like, why would you want to go to Facebook? They don't have a research lab. You're a research scientist. Why would you want to go there? He said, yeah, you're right. And then 2 weeks pass, and he calls me again, and he says, I've talked to Mark Zuckerberg twice. I say, what? You talked to Mark Zuckerberg? He said, yes. And, it's really interesting what they're trying to do. I think I'm going to take the job. I'm going to move from Google to Facebook. And so that was a bit of a shock, because I knew Mark Aurelio really well, and I knew he wouldn't go there unless there was some really definite, will to kind of get into serious research. And so he joined at the end of August, I think, of 2013. And then a month later, I get a call from Mark Zuckerberg. And, he, again, a bit like Schrep, kind of wants to get the lay of the land. So try to figure out, like, how can we move forward? And then he asked me, can you help us? I say, well, I'm not going to work for Facebook because I don't want to move to California, and I want to remain a professor at NYU. I don't see myself kind of leaving this. So, I can help you, but I can't, like, be a Facebook employee, right? I said, okay. And then, the company kind of goes into sort of several trials, several attempts at kind of getting this jump started, and then realize after a couple of months that basically the best way they have to start a real effort is to hire someone senior and kind of build a research lab from the ground up, rather than, say, acquiring a startup or something like that, right? And so I had to go to California for the pre-NIPS CFAR workshop that you've participated in a few times. And Mark Aurelio was going there too, so he knew I was going to California. So he said, like, why don't you drop in at Facebook and see what we're doing? I said, sure. And then the next thing is I got a call from Mark's assistant saying, why don't you come a day earlier and have dinner with Mark? I said, sure. So I get there, have, one-on-one dinner with Mark at his house, and he tells me what he wants to do. And I find it really compelling. And I realize that he knows a lot about machine learning. He's read everything there is to read. He's read some of my papers, which completely floored me. He at Facebook, he's sitting, nobody has offices at Facebook, right? It's all open desk, right? So there is a little block of 6 desks, and there is, Mark Zuckerberg, Mark Schrepfer, the CTO, and just across from Mark is Mark Aurelio.
Your former student, right there.
That's right. Who is like the first, AI researcher hired at Facebook. And the reason is because Mark wants to learn about AI, so he keeps coming to Mark Aurelio. And at the end of the day, he says, okay, we just want to hire you somehow. Like, can you build a AI lab for us?
Wow.
And I said, well, I only have 2 conditions, which is that I don't quit my job at NYU, and I don't move from New York.
You really love New York. Yeah.
And Mark says, sure. I said, okay, what do I sign? it's not like that. It took 24 hours, but but I was given a chance to create a research lab from scratch, and I had some I've thought about this, before, because I'd worked in industry before, at Bell Labs and AT&T and
so I'm very curious. What kind of mandate did you get? Because when you're a professor, you're in charge of everything you do effectively.
Yeah.
It's your lab, you do whatever you want. But when you run a lab at a company, well, you're hired by the company, and the university hires you and has expectations. It's very different. Your research is completely free. Most of what you do is pretty free. Companies have expectations. So what was the mandate? Well,
so there were demands. There were very little demands from Mark and Shrep. They were pretty convinced that a research lab would produce something useful in a reasonable amount of time, even if the goals were very long term. And I really believed in this too, because that's kind of the story of my career. Trying to build an intelligent machine and then kind of working your way back. And whatever you come up with, the first step you come up with turns out to have applications like convolutional nets, right? Or backprop or whatever. So I kind of explained that. I said, we're going to have very ambitious goals, very long term, and they wanted that. But at the same time, things will fall out of it pretty easily, and we need to kind of organize this in such a way that this can be picked up and be useful for the company. But I think there's two things that are really important if you want to this to succeed. One, there has to be a lot of freedom on research scientists on the topics that they pick to work on. It has to be essentially bottom up. Okay, you can do it top down, but top down is more kind of directed research. And it's going to be much more difficult to attract high quality people in this kind of environment. So if you want to attract the top people, it has to be completely bottom up. And then the second thing is that the research has to be open. Okay. And I struggled with the openness when I was at Bell Labs. So Bell Labs, you could publish just about anything, but everything had to be patented, and you could not open source code. It was it was before the time too, but it was really difficult. You have to go through layers of lawyers. It was really difficult. And I said, I told Mark and Shrep, if we practice open research, first of all, it's going to be much easier to attract good scientists, because the currency that measures the quality of a scientist is or her impact, intellectual impact, right? And that goes through publications. That's one reason for publishing. There are other reasons. The published research is also more reliable. It's also easier to convince people inside the company that the stuff you produce is good if it's published.
It's the state of the art. It's the best system out there, right?
Right.
If it's published and reviewers label it state of the art, you know it is.
That's right. And so the answer was astonishing but wonderful. It was, oh, you don't have to worry about this at all. We come from the open source world. Shrep's previous job was, tech lead at Firefox. He said, it's on our DNA. We open source stuff all the time. We don't even patent anything except for defensive purpose. And even that comes with an open license to anyone who wants to use it. So we never sue people for using our patents. So I said, oh, that's awesome.
And I fast forward to just a few months ago, and I have a quote from you in the next web that says, you take AI out of Facebook and basically the services crumble. So in 2013, AI got started there. Now it can't work without it. Can you say a bit more about that? A lot must have happened in those years, turning AI from this nerdy research conference kind of activity into real world creation of value. And what happened?
Right. And by the way, that's true of Google as well. Okay. You take deep learning out of Google today and it crumbles. It's entirely built around
maybe
it.
More companies than even, yeah. Wow.
I mean, there's lots of companies that are built on this, but these are the most, the two most prominent ones. So what happened was, so the first applications were, convolutional nets essentially, used for image classification and face recognition. So face recognition is really useful because on Facebook, you're in a picture that a friend of yours posts, and you get recognized in it, and you get sent a message. Do you want to be tagged? You happen to appear in a picture, so you get this kind of automatic tagging, and people get alerted whether they are in a picture or not, which is kind of good. So that was probably one of the first deployed application. And then another one was a kind of internal product called X-Ray, which was a system that would, take an image, extract, like run a convolutional net, extract the feature vector out of it, which is, basically a long list of numbers, and then just store it somewhere. And this could be used to tell if the picture contained, various things like, does it contain people? How many people does it contain? Does it have a car in it? Maybe what's the brand of the car? Does it have weird things like weapons or, things that are obviously kind of drug related, or is it terrorist propaganda? Is someone getting their head cut off? Kind of horrible things that you want to.
Sounds like a lot of things that we normally don't see when we're on Facebook, but that behind the scenes, that system is seeing and then maybe removing or something.
Right. And it took years before the system was, progressively deployed and actually worked, like to detect, nudity and violence and, neo-Nazi propaganda, all kinds of stuff, right? That are either, and child exploitation. I mean, there's all kinds of horrible things that people want to use Facebook for, that Facebook has to.
What fraction does the AI see and remove? Like, is the bulk of stuff that just needs to get removed, or is it?
Right now, it's basically all of it. Like for image stuff, it's basically all of it is AI based. Yeah.
All of it gets seen by the AI, but then is it like 90% is garbage that needs to be removed, or is it?
Yeah.
It's dominated by things that need to be removed. Wow.
No. I wouldn't say 90% of the material on Facebook is garbage. It's not. No. I mean, it's still a relatively small proportion that has to be taken down. But most of it is being taken down automatically. Maybe
because it's taken down so effectively, it becomes less meaningful to post it because it doesn't go anywhere. So.
Right. And people play games, right? So so now there's also kind of text understanding systems that try to figure out, is this hate speech? Is this call to violence? Things like that, right? Or is it things that are illegal in certain countries, right? In most European countries, there is, hate speech is actually illegal, right? It's not just that Facebook doesn't want it; it's that the government doesn't want it. Okay, I mean, it's not just the government; it's like
So, is it possible that if you took the AI out, that effectively people who want to post those things would notice it's gone and start just flooding the place?
Oh, absolutely. And there are social networks where that happens today. Like, 4chan, 8chan, Parler, those basically advertise themselves as not regulating content, but they end up being a cesspool of
completely different kind of content. Right.
Yeah. And then sort of became so only in the last year or so, with the progress in natural language processing, basically due to self-supervised learning, transformers and BERT and things like that, right? That's, some of which originated at Facebook, but, some of those ideas came out of Google, and we exchange ideas. That's the beauty of open research, which is that those ideas actually circulate really quickly. Now, 95% of hate speech or so is taken down automatically, without anybody seeing it. And this went from, essentially 0% 2 years ago, maybe 20% 2 years ago to,
There's a big difference as AI gets more precise. It becomes a lot easier to put to work.
Right. And then there is translation. Translation works really well. So, Facebook is about connecting people. One of the best things you can do is erase the linguistic barriers. And, the recent progress in translation have been completely astonishing. That's probably one of the coolest work that has happened in AI community, in particular at Facebook, over the last few years, is the fact that you can train multilingual translation systems that can translate from 200 languages to 200 languages from any pair, any direction, and those are trained with very little data. And you don't have to go through English or anything. The system can develop their internal representation of language that's sort of independent of the particular language you're using. I find that really astonishing. There was some really amazing work also by Guillaume Lample and Alexis Conneau, who were actually resident PhD students in Paris on completely unsupervised translation. So you you can represent, as I said earlier, you can represent. Say again?
What is completely unsupervised translation?
Okay, so here's the idea. I explained that there are techniques where you train a system to predict missing words, right? And with those techniques, you can train a system to represent every word by a vector, a list of numbers, right? So you train that for a language, let's say English, okay? And you do the same for another language, let's say French. These are bad examples because there is lots of parallel text in French and English, but let's use that pair for the sake of simplicity. So an entire language now is a cloud of vectors. Vectors are kind of like points, if you want, right? So all the words in the language is a cloud of those points, right? That has particular shape. And so English is a cloud of point, and then French is another cloud of point. And now what you're going to try to do is try to kind of transform those two things so that the two cloud of points match. The shape basically match, right? So you kind of align them on top of each other. And what emerges out of this is a mapping between English and French. And so now you can build a translation system. It's not a record-breaking one, but it's a decent one. And you never had to use any parallel text,
right,
of English and French. You never had to have a Rosetta Stone or anything. You just have English on one side, French on the other side, and just the structure of language is such that you can build this translator. I find that absolutely astonishing.
That is amazing. And as you go through these things, it's clearly a lot of AI is being deployed at Facebook, but Facebook can't be unique in the sense that it's the only company that is deploying AI. Many companies out there are deploying AI for their own needs. And I'm kind of curious if in the last few years, if you've seen a shift in terms of really how, even because at Facebook, you're interacting with the CEO of the company, which is very different from typically as a researcher, you are in your own world. You're not necessarily interacting with the CEO of the company, right? And at Facebook, are there places where have you seen AI play a much more strategic role in how companies make product decisions or make investment decisions and so forth? And anything you can share about that?
Oh yeah, absolutely. So this is not just the sort of default services that Facebook offers. Ranking the newsfeed, doing ads, translating, filtering objectionable content, all that stuff. There's also, products that Facebook, physical products that Facebook puts out, like the Portal system, which is a video conferencing system. So the Portal system has a smart camera, which is basically a wide-angle, high-resolution camera. And by software, the camera can zoom on the speaker, or if there are multiple speakers, kind of widens, and it can pan. And it's basically like a camera operator, and that uses AI, or it uses convolutional nets for detecting people, figuring out which way they're looking, all that stuff, right? Then there is another set of products that are heavy make heavy use of AI, which is virtual reality glasses.
Mm-hmm.
So virtual reality,
entirely new product lines based on AI that didn't exist.
That's right.
Before.
So, inside that tracking of you wear goggles, and the goggles has to figure out where you are in the world and track your position accurately so it can render the world from the right point of view when you move your head. And traditionally, there would be cameras, infrared cameras that would be looking at you and try to kind of figure out the geometry of it. But now the way it works is the other way around. You have cameras on the goggles. You don't need anything external. And the goggle looks out and tracks its own position. And that's using kind of, feature detection and all that stuff, that some of which is based on deep learning.
It's kind of interesting. What you're touching upon here is also a system that would not be purely in the digital world anymore. Something I'm personally very excited about is getting AI to work in the physical world with robots or other ways in the physical world. This is physical world observations, real-time physical world observations. I'm curious more generally about your thoughts on bringing AI into the physical world. I know you've worked on some projects in the past for not car driving per se, but vehicles going across complicated terrains based on vision and so forth. So what do you think, for example, about self-driving cars?
Right. I actually have a project on self-driving car. I'm working.
Oh, you do?
Yeah, it's a project with NVIDIA.
I didn't know you were involved in the NVIDIA self-driving project. That's exciting. So you might have some very precise thoughts on self-driving cars.
It's an interesting story, actually, which I can tell you. When we were working on robotics, this was a DARPA project called Lager, which you probably heard about. I think you were still a student with Andrew when that happened. Yes. And Andrew was involved in this separate project about robotics from the same project manager. And my group at NYU got associated with a small company in New Jersey called Netscale Technologies, which where the CEO and founder was a former colleague of mine at Bell Labs who had worked on convolutional nets when he was doing his PhD in Switzerland, a guy called Urs Müller. So they were kind of, Netscale was kind of doing a lot of the kind of development for Lager, and my group at NYU was doing a lot of the sort of upstream research, and it worked really well. We had a couple of projects like this, and then the deep learning revolution happened. Things started to pick up, and I get a call from Elon Musk saying, we need to build our own sort of AI self-driving system because the stuff we have from Mobileye is not good enough, and they don't want to work with us anymore. So, how do I go about this? They say, well, you should talk to my friend Urs Müller. And then a week later, I get a call from Jensen Huang from NVIDIA, who says exactly the same thing. Says, we'd like to sell our hardware to, for autonomous driving to car manufacturers, but, we can't sell them anything unless there is a whole stack on it. So we need to build our own autonomous driving stack. How should I do about this? Well, you should talk to my friend Urs Müller. And so Urs, within a week or so, interviewed both at NVIDIA and Tesla, and NVIDIA was just faster, so to make him an offer. So he joined NVIDIA, and then he's based in New Jersey. In fact, he's in the very same building that we used to work at Bell Labs, which is now kind of another. He's even in the same corridor. It's kind of
okay. So we're talking about self-driving cars, and that's real world, physical world, but there's actually also a lot of impact on what we do in the digital world on our real lives, right? And curious how you see the future of social media as AI becomes ever more capable, right? How do you envision that will shape social media?
I mean, the role of social media is to connect people with each other, right? Erase cultural barriers, get people to understand each other better. I know there is some belief among a lot of people that social media is the cause of polarization, political polarization, for example, or the dissemination of conspiracy theories. But that's actually not true, in the sense that, first of all, even if it were true, it would be sort of, seeing negative effects and ignoring all the positive effects of social media, and there are many. But it's probably not true, because the polarization is observed only in certain countries like the US and the UK, for example, but not in other countries that use Facebook just as much, or also other social media just as much.
One could maybe distinguish between causing, which is one thing, and another thing, which is providing a fabric that, if people are so inclined, makes it easier for them, right, to polarize. And it seems some of that is happening, right, where it's a fabric where polarization seems easier to happen than the fabric wasn't there.
There's a huge difference, though, between traditional media, which are one way, and social media, which is two way. So when some crazy, wingnut extremist delivers a message on, some extremist TV network or radio, which is one way, there is no response. There's no one to
feedback
to say. There's no feedback. There's nothing to tell the audience this is BS, or this is wrong. This is factually wrong. Blah blah blah. Whereas in a social network, there's some crazy post by a famous person. If you're not, connected, you'll just see that thing. But if you read the comments, there's going to be a lot of discussions about how this is wrong and how this is, incorrect factually. There's going to be a little thing at the bottom that says that fact is actually disputed by our fact checker. Click on this if you want to know more. So the fact that you can respond, the fact that the communication is two-way is the essence of democracy and free speech, which you don't have in traditional media. So if I were to look for a cause for polarization, I would look in traditional media that disseminate conspiracy theories. And social networks work both ways. Conspiracy theories can disseminate conspiracy theories, but also other people can debunk it just as well.
One part that maybe stands out to me about social media is that it's in some sense one of the places where AI is the most active in our worlds, right? Mm-hmm. Self-driving, sure, safer cars, but most of us are in social media, and it's driving a lot of our interactions. And under the hood, these interactions are AI is making decisions, right? Because I cannot see everything. Well, I don't want to see everything, because that's why Facebook, for example, built the news feed. I would find it too boring to see everything people post, and then it helps decide what I'm interested in. And it seems like those decisions, as an AI becomes better, there are all these stories about AIs building paperclips, right? And it's like, okay, if you ask an AI to build paperclips, it's going to turn the whole world into a paperclip factory. And in some sense, it seems this is, in some ways, sometimes a microcosm of the same idea. When you ask the AI to do something, for example, we want people to spend more time on Facebook, or maybe we want them to click on more ads, or maybe some other objective. Whatever the objective is, some objective gets set by somebody.
Yeah.
And if it's not exactly right, and the AI is really good, these things can get out of control, right?
Yes.
And so I'm curious about your thoughts on those things. Even just a simple thing of, should we really be spending maximal time behind our computer, right? Is that really the goal?
I probably spend, more time on social networks than a lot of people, because I use it as a platform essentially for disseminating a lot of, communication about science but also about society and politics and all kinds of stuff, right? But to respond to your question directly, so there is this myth somehow that the ranking algorithms that Facebook use for your newsfeed reinforces the stuff that you like, and therefore kind of creates information bubble. This may have been true in 2014. It's not true anymore. So there was some major, fundamental changes in the way Facebook operates, or the newsfeed ranking operates, around 2017 that, basically completely changes that thing. And people sort of remember the old Facebook, and they say, oh, this is why, Facebook is polarizing the world, but it's not actually.
It's still very hard, no? In that you must still be setting some objective behind the scenes. It's now a better chosen objective in some way. But fully optimizing an objective is always risky, I would say.
It's not risky, it's complicated, right? It's not as complicated as designing a system from scratch. Designing an objective function that the system will maximize is easier than designing the system itself, right? First of all. And it used to be that the newsfeed ranking system was just designed. There was no machine learning in it, back in 2014 or something, 13. Then there was a little bit of machine learning in it. And now, there's a lot of machine learning in it, but there's a lot of things also, the criteria that are being optimized have changed. So it's not maximizing the time that you spend. It's not maximizing, engagement or whatever. The ultimate objective is sort of meaningful interaction. So people have to be happy about the time that they spend on Facebook, and must have the feeling that they're not wasting their time. Because if you don't try to maximize this objective, people eventually are going to get bored and just do something else, right? They're not going to be on Facebook anymore. So that's really that's the ultimate criterion. Now, this is not a criterion that's really easy to measure. So you have to use proxies for that. And that's where it becomes complicated. We're very familiar with this in machine learning, right? We do this all the time. We replace the actual objective function we want to optimize by a proxy, a substitute, that is easier to optimize, but and can be computed, right?
Yeah, I actually do wonder, maybe reinforcement learning could play a role here, because
Oh,
you could
totally.
actually learn people and they could give feedback whether something was meaningful or not, whereas they might not be able to construct the meaningfulness themselves. So there might be some opportunities there.
Oh, absolutely. No, I mean, there is a lot of, reinforcement-like learning in there, which is, particularly, there's also causal inference. So there's a lot of like feedback loops, right? If you show something to someone, they're more likely to interact with it so you have exploration, exploitation, dilemmas and things like this. So yeah, I mean, it's,
So Yann, switching gears for a moment, but on the same topic, this is also the kind of thing where, as a scientist, we used to be in our own world, but now the things you build actually affect things in the world. And so to which extent do you essentially think about, hey, what is even the Facebook algorithm? What is it even optimizing? And are those things on your mind as an AI researcher at Facebook to really think about how it is being used beyond just building the next technology?
Right. So it's something that I am interested in as a personal interest, but I'm not actually working on this for the company, and basically no one at FAIR is. We develop basic machine learning and AI technology and image recognition and natural language understanding, translation, all that stuff, right? And some more core machine learning techniques, as well as tools and things like this. And then it's in the hands of the people actually designing the products to figure out like what are the good objectives, what are the, things like that. And it's, somewhat removed from what we're doing. Of course, we can interact with them, we can provide advice, we can, give ideas about like new ways of, assessing the reliability of a post, for example, to figure out like how to rank it. But this is really completely outside of our purview. But of course, we have a responsibility if we have good ways of helping with this to actually do it.
But what if you're not sure that the people who set the objectives are setting the right objectives? Do you want to send them that better, more perfect optimizer?
Well, if it's something that you know about, so there's stories like that about like, some kind of weird causal feedback loop in like ad placement or something like this, right? And, there might be an expert at FAIR who knows something about causal inference, who realizes that might be a problem. So that person might start, talking to the people doing ad placement and say like, you may not realize it, but you have an issue here that, the thing you're measuring is not the right thing actually because of this causal loop. So if you were able to do like, causal inference, you would be able to kind of tell apart, what really matters and what variable you can influence that are, causally influence the stuff you care about. So, I mean, there's all kinds of things like this that, there are technologies that were developed at FAIR that are used, just about everywhere in the company for things that are really important. So there's a piece of technology which is actually completely open source called FAISS. That means Facebook AI Similarity Search. That was developed at FAIR in Paris, mostly by Mathis Douze and Hervé Gégou. And Jeff Johnson. And it's basically, it's not kind of the traditional type of AI that you think of, like deep learning, but it's basically a very, very, very fast nearest neighbor search system. So here's a billion objects, vectors, and here is one object. Give me the 1,000 among this billion that is closest to this one in, I don't know, a few microseconds. This can actually be done. This is incredibly useful because you have, some extremist group posting a video or a photo of some, propaganda piece. And then you have all kinds of sympathizers, it's taken down, but there's all kinds of sympathizers basically modifying this video and then reposting it. And you have to detect approximate copies of it. There's blacklists, there's whitelists, there's things, and you have to do this for everything that people post. This is, hundreds of billions of things per day. And you have to, check against kind of, blacklisted content and all that stuff. This is the kind of stuff that needs to be done. I mean, there's incredible technology behind it. People don't realize like how much technology is behind a service like Facebook.
The amount of AI happening behind the scenes is enormous. And there is people in the loop. And what I'm curious about is how do you see kind of longer term the synergy between AI and humans? And maybe especially also how you might see something like a home robot or something like that emerge. And,
Right.
and how do humans and robots go together?
Right. So, one of the big kind of dream of both AI researchers and a lot of companies is an intelligent virtual assistant that, can help you in your daily lives, and you can, ask any question and keeps you out of trouble, and, organizes your information and your flow of information, your email, whatever means of communication. It displays stuff in your augmented reality glasses, wherever you go, tells you the name of the people you're seeing, whose name you don't remember. So all the stuff, right? Many of us have seen this movie, Her, right? You've seen that movie, Spike Jonze movie.
Mm-hmm. Yep.
It's actually not a bad depiction of what a truly intelligent virtual assistant, might look like in the future. I'm not clear about the whole love story and everything, but that is not necessarily a bad depiction. And this is something that a lot of people have in mind. And so there's going to be a future where, people are going to wear augmented reality glasses, and they're going to have, intelligent virtual assistants that help them in their daily lives, and they're going to be based on AI. And so before that happens, we need AI that has common sense, that can hold a dialogue, that knows how the world works, that kind of understands everything about us. And they're going to be our own personal assistant, just specific to us. We're going to train that assistant to work for us. Okay, it's going to be our kind of specific to each of us individually. So that's kind of, in my opinion, the future. And then there's the physical embodiment of this, which is, either, domestic robots that, do everything in our houses, and our cars that drive themselves and things like this. And the question is whether the virtual personality of those virtual assistant is going to kind of migrate from our domestic robot to our, AR glasses to a car, or whether it's going to be a different personality every time. That's kind of a question. But we're very far from having the technology to be able to do those things. This is not going to happen. It's going to take at least a couple of decades.
As I think about the future and what AI itself will look like in the future, the thing under the hood, the thing that would be driving the robot brain effectively, or the digital brain in our computer. Recently, Jeff Hinton, who of course you're great friends with and have known for a long time, one of the other pioneers of deep learning, he said, I think deep learning can go all the way. We won't need a fundamentally new paradigm. Deep learning is not today's deep learning. We'll need more breakthroughs within this realm of deep learning, but we don't need a completely different thing.
Right.
What are your thoughts on that?
So my version of that statement, which I think is pretty much what Jeff means as well, is that the basic idea of deep learning is that you construct a machine by assembling parameterized functional block. I'm using a technical term here, but bear with me for a minute. And then you train it from example, end to end using a what's called a gradient-based technique. So a technique that can estimate in which direction you have to move all the adjustable parameters to get the answer you want. Whether the learning is supervised reinforcement or unsupervised, self-supervised, doesn't matter.
Maybe all of it.
So
yes.
Maybe all of it at the same time. So this idea that you build a machine by assembling those blocks and you train it using gradient-based methods is here to stay. Okay. So whatever solution AI is going to be even 20, 30, 50 years from now is probably going to have this idea as an essential component. That doesn't mean that whatever we have today is sufficient. Like, we don't know how to do self-supervised learning that deals with uncertainty, for example. This is something we need to solve. and it's probably going to be part of the solution. But the basic idea of deep learning is here to stay. I don't see it disappearing. So this is my opinion, but it's also, I think, my interpretation of what Jeff says. He says, whatever we do in the future, whatever AI system we're going to build, this basic idea of deep learning is going to be part of the solution.
It's pretty wild. Definitely, when I started my PhD in 2002, I would not have imagined that AI researchers would get called up by the CEOs of the world's biggest companies and be asked any questions about anything. And there you are, being called up by Elon Musk, arguably the most visible CEO in the world these days, and CEO of Jensen Huang of NVIDIA, asking you the same question within a couple of weeks' time. I think that's just amazing. But given that you're also working on this, we know Elon said there will be Tesla fully self-driving taxis by the end of 2020. Well, it's 2021. That didn't happen. That was optimistic, let's say, right?
Well, none of us in the business believe that, right?
Well, I don't even know if he believed it, but he did set it as a goal at the very least. Did try.
I don't know, but there was a dinner organized by Mark at his place with Elon and Schrepp and a few other people to basically discuss with Elon, like, what is, that's at the time that we were saying we should regulate AI because it's going to kill us all, right? He had this period, right? Mm-hmm. And Mark was kind of concerned by that and really wanted to get the idea of why he was thinking this. And also we're kind of hoping to kind of change his mind about it because we didn't think that was really the case. And it was pretty clear to us that he was very optimistic about the speed of progress. That he thought, I think he had bought the original kind of marketing pitch or sales pitch from DeepMind and various other companies that said, "Oh, we're going to have AGI within 5 years." And
that didn't happen yet.
It didn't happen. I mean, we're now like 6 years after that, and we're still, nowhere close to human level AI or even cat level AI for that matter. I don't think AGI exists. I don't believe in the concept of AGI because I think human intelligence is actually very specialized. So I don't think general intelligence is something we should be talking about.
AGI is different from human level intelligence. Those are two.
Yes. Yeah.
So AGI stands for artificial general intelligence. And a lot of people associate that with the notion that AI becomes as smart as humans. And then because it has more compute power, it'll quickly exceed the capabilities of humans.
Right.
The brain is limited. It's only so much energy can do compute in your head. And the AI can use the entire world of compute in principle, right? But you're saying AGI, artificial general intelligence, and human level intelligence are very different things.
Human intelligence is very specialized. We don't like to think of ourselves as being so specialized, but we are.
I see. So you think of us as very, very specialized. So, some people would say we're very flexible, though, compared to...
We're flexible, but we are specialized. Here is a way how we are specialized. There's a lot of things that computers do much, much better than humans. And so it must be the case that humans are not very good at those things. Like, let's take the example of chess and Go playing, or poker for that matter, where, machines, now overtake humans in all of those games. There was this idea somehow before, good Go players that humans were very close to an ideal player, maybe, to God, right? Like 2 or 3 stones handicap or something like this. It turns out, no, humans are absolutely terrible at Go. Machines are like so much better than humans. And so, we thought of ourselves as being almost kind of ideal and divine. We just suck at Go. We are horrible. And so there are many things like this where humans really are bad.
But there's also this notion, I would say, that humans can adjust. And I think that's what a lot of people think about when they think about artificial general intelligence, this notion that humans can learn new skills. That maybe...
Yep. Learning is part of intelligence.
Maybe there's a board game you've never seen before, and somebody explains it to you, and you now know how to play it. You might not be the world's best player, but you understand the rules, and you can take joy in it, and become better over time and enjoy that experience. And I think this flexibility of learning something new is quite special, right?
Yeah, but it's limited. It's limited flexibility. So let me take an example. If it's a well-known experiment that was carried out by a few people, I think at MIT, where you wear glasses that have a prism in them, so that the image you receive in your eye is flipped. Okay, so you see the world upside down, and you can adapt to this very quickly. I mean, in the space of a couple of weeks, it's now natural for you to wear those glasses, and when you remove the glass, all of a sudden now the world looks upside down. Okay, you readapt to it much quicker, but so there is adaptation in that sense. But let's imagine another experiment where through some process, fiber optic or electronics, the glasses you're wearing or the goggles do a random permutation of the pixels in the image. Okay, a fixed permutation, but random.
Complete scramble. If you're looking at a screen, it's completely scrambled. Okay,
that's right. Will your visual cortex be able to adapt to this? And the answer is probably no. I mean, you might be able to recognize a few things, very low resolution and things like this, but it's going to be a complete mess. And the organization of your visual cortex is such that there is no way you can catch up. So, okay, it is an extreme example, but it shows that.
So you're saying that's an example of specialization that our brain, as you alluded to earlier, when we're children, we actually learn a lot. And maybe a lot of that learning is in our brain consolidating the sometimes geometric structure of the world. And so if you now scramble an image, we can't make sense of it anymore because we've been trained to expect a certain structure.
This is not training. Even if you do this with two children, which would be a horrible thing to do, unethical. I don't think children can.
So it might even be evolutionary. It might evolutionarily be in our brain that we have certain structure.
The reason for this is the reason why I started working with convolutional nets, right? So the reason why a convolutional net is a particular type of neural network whose architecture is inspired by that of the visual cortex, and the characteristic of it is that a neuron in the early layers of a convolutional net is influenced by a small area in the image. This is called local connections or local receptive fields. This works if nearby pixels are correlated. So if the pixels are organized as in a regular image, there is an advantage to having this local processing. But if you scramble the pixels in a random permutation, you break this correlation and your local feature detectors basically are useless. So that's, it's the hardwired architecture of the visual cortex that will prevent you from being able to do vision with scrambled pixels.
When you think about neural networks, most people will easily think about the brain because don't we have neurons in our brains? And our brain also has this general capability of reasoning about many, many things. So maybe you think, yes, neural networks should be good. Can you say a little bit about how the neural networks that you are building, other people are building, relate to our brain?
So they relate to our brain in the way that airplanes relate to birds. So birds and airplanes use the same basic principle for flight. They both have wings. They use very, very different ways of propelling themselves to air, but they use the same principle to generate lift from by propelling themselves through air. So it's a bit the same thing, right? The general kind of idea between neural nets and the brain is kind of the same. It's this idea of lots of very simple elements that are connected with each other, and whatever behavior comes out of it is kind of an emergent behavior that comes from the complexity of the network. And the way those systems learn is by changing the efficacy of the connections between those nodes, right? So that's the general idea. Now, if you dig a little deeper than this, the analogy stops. So the same way airplanes don't flap their wings and don't have muscles, those neural nets don't work at all like the neurons in the brain. In fact, some people say we shouldn't call them neurons at all. And the type of learning that we are able to reproduce in machines is very different from the type of learning that we are observing in biology. So the type of learning I described before, where you show an image to the machine and you tell it the answer, and then the machine adjusts itself to get the answer closer to what you want. That's called supervised learning. And it works really well if you have lots of data. So you want to translate one language into another, you collect millions of sentences that have been translated from one language to another, and you just train the machine to kind of do that. And speech recognition is the same. You can have tens of thousands of hours of transcribed speech. Image recognition, you can have millions of images, but it only works for things for which it's feasible to collect that much data. And there's a lot of situations where it's not feasible. Like you want to identify tumors in certain medical images, and you just don't have that many of them because perhaps the disease is rare and it's very different every time it shows up. So there are a lot of situations for which it's just not feasible.
But also, you refer to this notion of supervised learning. What does that mean exactly, to be supervised learning?
So supervised means that you show the system an input, let's say an image, and you tell it what the correct answer is, and it adjusts itself so that it produces the correct answer. Then there are two other types of learning. One that has become quite popular in the last few years, and you, Pieter, have been working on this since you were doing your PhD, called reinforcement learning. So, yes. And I'm going to teach you about that. But the difference is that you don't tell the machine what the correct answer is. You only tell it whether the answer it produced was good or bad. And so if the set of answers is really large, the machine has to basically kind of try many things before it figures out the correct answer. This is very good for training a machine to play games, for example. But it's very inefficient in the sense that it takes a very, very long time for a machine to learn anything useful. Like training a robot to, grab something or to drive a car. It would take too long if you used at least the current brand of reinforcement learning, or until,
because it has to stumble upon the solution before it learns about it being the solution. It has to discover it's on its own. So it's a very different kind of learning.
It has to do millions and millions of trials, and also what it's going to see next depends on the decision it just took. So that makes things even more complicated. And then there is a third type of learning, which is in my opinion, the primary type of learning that happens in the brain in animals and humans. And I call it self-supervised learning. People call it lots of different ways, but it's basically a type of learning where the learning system, whether it's a machine or biology, basically learns to represent the input without learning a particular task. It just learns the general organization of the world, if you want. And if the machine can train itself to do this, then learning a particular task can build on top of those representations learned by the system just by observation. So human babies, and this is true for most animals, learn how the world works in the first few months of life essentially by observation. And most of what we learn in our life, we learn in the first few months of our lives. We get the impression that everything we learn in school and to our parents and, at university by reading books. But no, actually most of the basic things that we learn about the world, we learn in the first, maybe 9 months of life.
It's a lot more relaxed version of learning in those first few months, is my impression. If I can remember anything of it, it feels learning in school is much harder work. Any way we can extend this kind of early childhood learning process a bit longer and keep learning at that pace?
Well, yeah, I mean, at that time, your brain is, very malleable, and, a big chunk of your energy is devoted to, everything is new in the world, right? When you're a baby, everything is surprising. You can only take a few hours of this a day, and you have to sleep on it to kind of reorganize your brain, every time, because it's completely overwhelming. But perhaps one principle that is used by biology to learn how the world works is through prediction. So there's a lot of internal structure about the world that we learn by training yourself to predict lots of things that we can't directly observe. Like just now you can't see the back of my head, but you have a pretty good idea what it looks like because you've seen a lot of people and etc. You can't predict if I'm going to move my head to the right or to the left, in a second, but you can predict that my head is not going to jump suddenly 30 centimeters to the left, or is not going to be upside down just all of a sudden, because you know the constraints of the physical world. You know that if I hold an object and I let it go, it's going to fall, right? Babies learn this around the age of 9 months. They learn about the fact that unsupported objects fall because of gravity around the age of 9 months. It takes them all this time to figure out the physics, if you want, of intuitive
9 months
physics
to
of
learn objects fall. Wow. Okay.
Right.
So we're learning fast, but maybe not that fast either.
Well, but once you've done this, you know, you turn 16 or even earlier than that, and you now need to learn to ride a bike, and you can basically learn that in half an hour, you know, with just a few trials without hurting yourself too much. You want to learn to drive, you can drive pretty well with about 15 hours of training for most people without ever crashing. We can't do this today. If we could solve that problem today, then we would have level 5 autonomous driving. We would have, you know, cars driving themselves without crashing anywhere. But we really don't know how to do it.
So this reminds me actually of something you're very well aware of, something called Le Cake, of course. And it reminds me of, this was NeurIPS 2016. You gave the opening keynote, kicking off the conference. This is, for context, this is the main machine learning conference, the biggest one. Pretty much everybody who works in machine learning goes there to share their work and see what other people have been up to and exchange ideas, get new ideas. And you kicked off the conference with the invited keynote where you introduced this concept of Le Cake. And as I was listening, I was sitting in your audience at the time, I was listening to it, it occurred to me that in some sense, even though my own path, which has been more robotics driven, and your path has been more pure machine learning driven, though we both touched on both sides quite a bit, that in some sense what you were presenting was the future of robotics. Maybe not the future that we're going to get right away tomorrow, but the kind of longer term, like what the most capable robots of the future might look like on the inside, how their brain gets built. So can you maybe say a little bit about this Le Cake idea and how it could play into robotics?
Right. So it's a metaphor that I used because I was seeing a lot of excitement for deep learning in the community, and deep learning at the time was, 95% supervised learning, and there was a lot of mounting excitement in reinforcement learning, and there were some people who thought maybe, perhaps naively, or perhaps they had some good idea that, by scaling up supervised learning, collecting more data, having bigger machines, or by scaling up reinforcement learning, we were going to, be able to create intelligent machines. And I was really convinced that that could not possibly work, that the way forward to really build intelligent machine was to get machines to learn how the world works and perhaps acquire some sort of common sense. And it could not be done through supervised learning and reinforcement learning alone, because the amount of feedback information you give the machine in supervised learning and reinforcement learning is very, very weak. It's very small, right? When you train supervised machine to recognize images, you tell it it's a car, it's an airplane, it's a person, it's a table, it's a chair. You give it just a few bits of information at every sample. So the amount of stuff that the system learns is limited by, how much information is in the label, which is fed by humans, and it's very limited. In reinforcement learning, it's even worse, right? The machine only gets a single number every time you try something. You're doing good, you're doing bad. Mm-hmm. Right. So the amount of trials the machine has to do is just enormous. So if you want, learning to be efficient, the machine has to basically figure out how the world works by itself. And so my analogy was, if intelligence is a cake, the reinforcement learning has so little information you give to the machine that's going to be just a cherry on the cake. And reinforcement learning is the icing on the cake. But the bulk of the cake is self-supervised learning, or whatever it is that humans and animals are doing. The joke I usually say is that, a house cat has more common sense than the most intelligent of all our AI systems.
how can we do self-supervised learning and make our robots more naturally smart?
That's the question. You tell me.
I see. It's not solved yet.
Yeah, no, it's completely unsolved. I mean, there's been very interesting advances in that direction over the last 5 years, and there's been some success in some domains. So, for example, the most successful natural language understanding systems today, the most successful translation systems, so basically text processing, text understanding, are very heavily based on self-supervised learning. And it's self-supervised learning of the type that I was telling you about earlier, where you take a segment of text extracted from a book or whatever, or Wikipedia article, a website, you remove some of the words and you train a gigantic neural net to predict the words that are missing. In the process of doing so, the system learns to represent language, and it learns automatically to basically represent a combination of syntax and semantics. It has to understand. Like if I tell you a sentence, the blank chases the mouse in the kitchen, you can probably tell what blank is, right? Exactly.
Yes.
And that's because you know how the world works, right? You know that cats chase mice, and cats are inside our houses and stuff like that, right? If I say the blank chases the gazelle in the savannah, you can probably also tell what it is, at least within some region. So by training a machine to predict missing information and telling it after a while, well, this is the word that was supposed to be there, the machine basically learns to represent
supervised learning. Then aren't you supervising it by having the text that has the completion for the blank?
Yes. So it's basically the basic algorithm you use to train the system is a supervised learning algorithm, because you're telling the system the correct answer. But the reason why it's called self-supervised is that this information does not come from someone who has labeled the data manually. It comes from the input itself, right? So you take an input, you correct it, and then you tell the system, recover the original input. This, by the way, applies to not just text, but you can apply this to speech and images. It doesn't work as well in images. But it works astonishingly well in natural language processing, to the extent that it completely revolutionized the way people do natural language understanding and translation about 2 years ago. Every system now that you use, whenever you go to Google or Facebook, the translation, the system that ranks the items that you see, either search items or search results or your newsfeed, this is all done by this natural language understanding system that basically do this. You can ask a question to Google will answer, right? And that's based on, all of this is based on this kind of technique. So there's been this enormous success of self-supervised learning in the context of natural language understanding. And it has not yet completely translated in other domains like speech recognition or image recognition, although...
Why do you think that is? Why do you think it works better in language processing so far and not as well yet in the other domains?
Okay, I'm going to say something that's going to be very controversial, but it's because language is simpler. Language is we like to think as humans, we like to think of ourselves as humans as the only species that has, complex language, and it's, intimately linked with intelligence and all that stuff, right? But language is basically an epiphenomenon of intelligence. It's a lot of animals who don't have language that are almost as intelligent as we are, like orangutans. Orangutans don't have language because they are solitary animals. They're not social animals. They're almost as smart as we are. I mean, on the scale of smartness, right? They're very close to us. Language in this context, in particular context of prediction, language is simpler because the prediction you're making is you're predicting a missing word, and you can never predict the exact word, right? So the example I said, the blank chases the mouse in the kitchen is basically only one possibility. It's going to be a cat, maybe kitten or something. But if I say the blank chases the blank in the blank, there's many, many possibilities of what animal where, which predator and prey, right? And so the system cannot make an exact prediction, but what it can do is that it can make a probabilistic prediction. So it gives you essentially a score for every possible words in the dictionary. There's maybe 100,000 words in the English dictionary. You have this giant list of numbers that indicate kind of a score for every possible word. What is the chance that this word appears here? And so we have an easy way of representing the uncertainty in the prediction by a big list of numbers, essentially. But what if I do something else? What if I train the system where I show it a little segment of video and I ask it, tell me what's happening next? Like draw the frames in the videos that are going to happen next as a consequence, as that can follow this. There's an infinite number of possibilities. And an image is a very complex object by itself, but a sequence of video frames is incredibly complicated. And we don't know how to represent the uncertainty in the prediction in that context. We can't have a big list of numbers that gives us a score for every possible image that follow a particular frame. So the complexity, and I'm getting into sort of a technical issue here, but this is really what we're facing. We do not know how to represent uncertainty in sort of complex high-dimensional domains like images, video, audio to some extent. So we have to invent other techniques, and there are a few that are really promising.
But it also sounds like what you're putting out there then is a notion that if somebody can crack this, if somebody can actually represent possible futures in the video sense, meaning not in their own head, but somehow train a neural network to be able to do that, that neural network would maybe have some notion of common sense, at least some kind of notion of common sense, and be able to learn other things much more quickly.
Absolutely, because that system would be able to just watch the spectacle of the world and then, train itself to predict what's going to happen next, and then understand that, if an object is not supported, it's going to fall. But here is the complexity. If I put this pen on my hand and I let it go, you can predict that the pen is going to fall, right? Mm-hmm. But you can't predict in which direction. And every time I repeat the experiment, it falls in a different direction. Right? Mm-hmm. So that's the complexity of prediction, which is that you don't want the machine to predict a particular image. You want it to predict, the pen is going to fall, but I can't tell you in which direction. How do you represent this? That's what we don't know how to do.
It seems we as humans represent that, though, because when I see the pen on your hand and it falls, I'm not too surprised, even though I can't predict which direction it's going to fall. I'm not surprised that it falls, and not surprised that it is in some direction. And yeah, that was a plausible direction. Why not?
That's right. In fact, that's exactly how we know that babies, know something about the world. You show them a scenario that breaks one of those laws of physics, and you observe how surprised they are. You basically, you measure how long they look at the thing, right? So you show a little scenario where, an object kind of appears to be floating in the air because the support of it is not apparent, is hidden somehow. And a 6-month baby will kind of look at it for a bit and not really pay attention. A 10-month baby will go like this, right? and stay on it for a minute because, her model of the world is being violated, right? She knows that an object is supposed to fall if it's not supported. And here is one that floats in the air. So that's surprise is how we measure whether our model of the world is being violated.
We are dropping new interviews every week, so subscribe to The Robot Brains on whichever platform you listen to your podcasts. So Yann, I want to get back to some of the kind of future of AI research, maybe a little later in our chat here. What I was maybe hoping we could also touch upon a little bit is, if you're willing to share, is how do you start out growing up in France? And now you are here in the US. I mean, you moved a while back. How does somebody just is born and then later they are an AI scientist? What was that trajectory for you? When did you know that's what you want to do?
Okay, it's simultaneously simple and complicated. Okay, so I grew up in the suburbs of Paris in a middle class family. My dad was an engineer in the aerospace industry. My mom was a homemaker, but my dad was really an engineer at heart, and he taught me everything basically. But when I was a kid with him, he would build model airplanes. He built his own radio control system actually. He taught himself electronics.
This is a long time ago.
This is a long time ago. This is in the 60s.
Nobody knew how to do these things at the time.
He had built model airplanes, before that, but radio control model airplanes, you couldn't just go out and buy a radio control system. You basically had to build it yourself in the 60s. So he did that. He taught himself electronics. He was a mechanical engineer, taught himself electronics. And, and I was like watching this when I was a kid, and I was kind of, amazed. So I always had kind of this sort of, engineering kind of, virus basically infecting the family. My brother also kind of went through the same process. He's actually he's a research engineer at Google in Paris. He doesn't work on machine learning. He works on combinatorial optimization guy. But I got kind of exposed to science and engineering this way, and I was fascinated even when I was a kid by the appearance of intelligence in humans. I was interested in paleontology for that. And how did it happen that, humans evolved and became intelligent? Like, I was fascinated by that question. And then, what is intelligence and things like that, right? So I was fascinated by physics, by astronomy, by all kinds of stuff, right? So then, I was okay in high school. I was very good at physics. I was okay at math. I wasn't particularly good. I was good, And so, there's kind of a strange type of educational system in France where if you're really good at math and science, you go into one track, you go into those like 2 years of preparatory school where you just do math and physics, and then you take basically a national competition to get into the best engineering schools.
I've had some students from those programs. It's amazing.
Right. And I didn't go through this because I really wanted to do engineering from day one, and science. And my math teacher in high school convinced me that I wasn't good enough at math to survive that. I went through an engineering school that, basically goes right after high school, right? And it's a 5-year program. You do a lot of math and physics and everything. And I did like way more math and physics than, the average student in that school. I learned electrical engineering and various other things. But while doing this, I was interested in this mystery of intelligence, artificial or not. And I stumbled on a book, which was the transcript of a debate between Noam Chomsky, the linguist, and Jean Piaget, who is the Swiss developmental psychologist, who studied how children learn. So I was, fascinated by this. I read this book, and it was kind of a debate where Piaget and Chomsky kind of brought people to argue for their side. And on the side of Piaget was this guy Seymour Papert, who was a mathematician from MIT, and his talk, which was transcribed, was about the perceptron, which was one of the early learning machines from the 50s. And he says, the perceptron is a very simple learning machine, but it can learn surprisingly complex concepts when you train it, even though it's so simple. And so it's the first time I read about a machine that could learn. I was transfixed, essentially. I said, like, this is what I want to do. This is the answer. Intelligence is so complex. We're never going to be able to engineer it. It's going to have to build itself by learning. And in fact, I discovered, decades later that Turing had the same argument. He said, if you want to build an intelligent machine, you'd be better off trying to emulate the mind of a child so that, this child could learn the way a human learns. So I always thought learning was going to be part of intelligence. And then when I learned that people had worked on this, I decided to basically spend all my spare time kind of studying this. So I spent, days at a time in the libraries. There was no internet back then, right? We're talking 1980. I had to, drive to Versailles, where INRIA had this like wonderful library, which I gained access to. They were nice enough to let me in. And I would spend, the entire Wednesday afternoon, because I didn't have class then, kind of looking through the old literature. And what I discovered is that the entire literature on this topic stopped in the late 60s, around 1969, 1970. You couldn't find any paper from the US or Europe that talked about perceptron, neural net-like machine learning, after 1969, roughly. And I discovered the reason for this one reason for this was a book whose title was Perceptron by two authors, Marvin Minsky and Seymour Papert. So here was Seymour Papert chanting singing the praise of the perceptron, but he actually contributed to killing it.
How do you kill neural networks with a book?
Well, it's a theoretical book that says, here are the limits of those models. You can't, here is what you can do, here is what you cannot do with those models without, them being ridiculously large or whatever. And it's a very interesting book that I read multiple times right, at that time. They were not wrong. It was just that the results were overinterpreted. In the sense that some of the problems that they say perceptrons cannot solve or can only solve with a ridiculous amount of resources, first of all, are problems that may not be that interesting anyway, that you may want to do. There are problems that are essentially sequential, so you might want to use another type of machine to solve them. And second of all, the main limitation was the fact that the perceptron basically has a single layer of trainable weights, right? So you can think of the perceptron basically as a single neuron with a bunch of adjustable inputs, and everything else before that is fixed, and so that's a very dire limitation. And what the neural nets, more the recent brand of neural nets, from the late 80s, and backpropagation allowed to do was to train neural nets with multiple layers of adjustable weights. And that's, by the way, why we call this deep learning. It's called deep learning for the simple fact that those neural nets are composed of multiple layers, right? To differentiate them from more classical machine learning, where you basically only have one layer that's trainable.
But you didn't achieve that right away, right? You're sitting in these libraries in Versailles, apparently, and reading these books. That's still a long path to making neural nets actually work and where we are today. Right. What happened next? Right.
So I was like a sophomore or maybe a junior. It's a 5-year program in France, right? So I was in 3rd year or something like that. And the school I was at, called ACA, ESIEE, you could do independent studies. So I went to see a math professor, and they said, like, I'd like to work on this. Like, I want to like do a project. And say, yeah, this, that sounds like it could be fun. So I did a couple of those, and I was really thankful that this professor kind of helped me. I had access to the school's computers, which at the time were kind of rather powerful for undergraduate students. And so I started experimenting with sort of various learning algorithms, and I quickly discovered that really what needed to be discovered was a learning method to train those multilayer neural nets. This is what people didn't find in the 60s. This is what caused the failure, if you want, of the entire field. And that's what needed to be unlocked, essentially. And I looked for all kinds of ideas there. There were people who were working on this in various places in the Eastern Europe, in Japan, etc. And I kind of stumbled on this idea that perhaps if you were able to sort of propagate signals backwards to tell every neuron, like, here is what I need from you to get the correct answer, that could work. And I came up with some sort of really intuitive rule to do this that we would now call target prop. And then I talked to one of my friends who was doing a PhD in optimal control. And he was working on planning, and he told me about this technique called the adjoint state method. I don't know if, I'm sure you know about this because you are a control guy. So this is an algorithm that goes back to the 60s that was used, for example, by NASA to compute trajectories for rockets, things like that. And it's based on the idea that if you want to shoot a rocket and you want it to meet the space station, you start by kind of shooting it, and it's going to miss the space station. So you compute kind of a distance between those two things, and you kind of adjust the controls, the nozzle, the thrust, the direction at every time step, so that it gets closer. And you do this by basically propagating a signal backward in time. This is all done on a computer, right? This is the backpropagation. This is the same idea. It's the same mathematics that we're using to train neural net. Right? Yeah.
And so that's amazing. So you're working on this back in France. How do you end up in the US?
Okay, so I was I finished my engineering degree. My specialty was VLSI design, by the way, chip design. But as I told you, I took a lot of physics and also actually optimal control stuff. And I stumbled on another book which was about self-organization and something called automata network. And I discovered that there is a small independent lab in Paris composed of academics who had positions in universities, but decided to kind of get together in this like little informal organization called Laboratoire de Dynamique des Réseaux. So this means the Laboratory for Network Dynamics, and they were kind of studying those emergent properties of large networks of elementary kind of simple objects, like cellular automata and things like that. And I just called them up, cold call, said like, I'm interested in working on neural nets and stuff. Like, can I just hang out? And one of them says, "Oh, you should sign up for a graduate program right now, because the deadline is like 3 days from now." So,
oh wow,
or something like that. Or you're too late, but like I can get you in anyway, or something like that. Right? So I registered to this graduate program, which was sort of a weird thing because in France you have to do like a pre-PhD before you do the PhD. So this was the pre-PhD. And that's how I learned to do research, because otherwise I was kind of isolated. But no one in that lab was working on neural nets. They were working on a sort of other type of things. I had funding from my like a scholarship from my engineering school, so I didn't need any support. But I needed someone to be my official advisor to at least sign the paper. So one of the members of this lab, Maurice Milgram, I come to him and I said, like, you are the one full professor who can actually take me as a student. Would you take me? He says, like, I have no idea what you're working on. I can't help you at all with anything technical, but you seem smart enough, and I'll sign the papers.
So you got absolute freedom in some sense to work on
freedom, but also, a bit of I was kind of out in the cold a little bit. Kind of.
How do you connect with the more general research world then?
Right. So one thing that, from the first month, I sort of started hanging out with people there. So there was a scientist called Françoise Soulier-Fogelman, and she kind of started to get interested in neural net pretty early on, but she connected me with the wider community that was already working on this. In particular, she gave me a preprint of two things. One, which was the paper on hub-field networks. And the second one was the paper from 1983 by Hinton and Chenowski on Boltzmann machines. And I look at this paper, and back then, those papers were like published in obscure conferences. I think the Boltzmann machine paper was published at either CVPR or AAAI or one of those things. But you couldn't get those unless you went to the conference and brought the proceedings back, right? So they got a preprint somehow. They asked Hinton or whatever, and they got a photocopy of it. There was no email either. Okay, so it was all by physical mail. And I look at this paper, and they talk encrypted way. They talk about essentially the multi-layer training problem. Okay, so the Boltzmann machine algorithm was kind of the first credible solution to training neural nets that had so-called hidden units, basically units that are neither inputs nor outputs, but are somewhere in the middle. And I thought, like, this is exactly what the kind of stuff, I'm interested in. I absolutely need to talk to these people, Chenowski and Hinton. Like, they are my heroes now, okay? And they are in the US and I'm in France. And how do I do that? So it so happened that the Françoise and a few other people organized a workshop in 1985 in France, where they invited a lot of physicists who were really interested in neural nets at the time. There was a lot of theoretical connections with solid-state physics or condensed matter physics, like spin glasses and stuff, because of Hub-field. And so they invited a lot of different people. In particular, they invited Terry Chenowski. So unfortunately, Terry wasn't here for my talk. I was talking about this kind of target prop algorithm in completely broken English. I was absolutely terrified when I gave my talk because my English was so bad. And also I knew people would not understand what I was saying. Both for the language, because of the language, and because of what I was talking about. So he wasn't there for my talk, but he came, gave a talk about Boltzmann machines. And then I cornered him one of the afternoon and tried to explain to him what I was working on. He was working on NetTalk at the time, which was sort of one of the first big demonstration of what backprop could do. But backprop was not published yet. Nobody had heard of it except him, because he was friends with Jeff Hinton. And so he went back to the US and he told Jeff, who was working on backprop, also preparing the paper. He told him, there's a kid in France who is working on the same stuff we're doing. And then a few months later, another conference takes place in France in summer 1985, where Jeff Hinton now is a keynote speaker, where he talks about Boston machines. So, by that time, neural nets were starting to get like a little hot, and Boston machines were kind of seen as sort of a big thing. So he gives his keynote, and then he's surrounded by 50 people, and I can't get anywhere close to him.
Sounds like you today, except 50 would be a few hundred.
I mean, Jeff was pretty young at the time. He was like, he was not 40, right? He was like 37 or something. So anyway, he turned to the organizer. I was kind of far away, right? And he tells the organizer, do you know a guy called Yann LeCun? And I go, I'm here. Basically, he had read my paper in the proceedings, which was in, French, and kind of figured out this was about multilayer nets and backprop-like things. And so we said, like, let's get lunch together tomorrow. And we basically, then he told me he was working on backprop. And I told him, well, that's what I'm working on too. And we were kind of basically completing each other's sentences. So this clicked like, immediately. And so he said, like, I'm organizing a summer school next summer, 1986 at CMU. He was still at CMU at the time, said like, I'll invite you there. And that's where I met the entire community, right? So this was the first connection to summer school. Michael Jordan was there, and, Terry and Jay McClelland. And I mean, a lot of senior people now that you see in the machine learning community actually were there at that summer school.
Because now all these people are your longtime friends, but then you're a young researcher and you show up and all these people are names you've seen, but you've never met them before. No. How was it? I mean, I can only imagine it's a bit intimidating.
Well, it is, yeah, but particularly intimidating because my English was so bad. And so, in fact, my English was so bad. This is one of the reasons I connected with Mike Jordan, because his French is very good. So
I see.
His French was completely fluent, and he's kind of a bit of a Francophile. So we connected, immediately, and sort of became fast friends.
I think you got a good part of it. You got to coming to CMU and meeting Jeff Hinton and everybody there, which I think got...
Yeah. I mean, I met Jeff Hinton, earlier in France. But what happened is in 1985, in this first meeting in the French Alps that was organized by the member of this lab that I belong to, where all the physicists were and where I met Terry Sinofsky, I gave my first talk. And there was a guy in the audience, a young guy who looked like a cowboy from the Arizona. He had like he was dressed like, he had like big sideburns, and it was very strange. And this guy was very young, but he was asking very nasty questions to absolutely everyone. Like, there was, this very famous person giving a talk about their major research, and this guy would raise his hand and ask a question that would basically destroy the entire talk or put it in question. And so I turn, to my friend and say, oh, these guys, yeah, I mean, they're from Bell Labs. That's what they do at Bell Labs, right? Whenever you talk about something, someone has done it at Bell Labs 10 years earlier, or it doesn't work. And so I was kind of terrified by this guy. And I give my talk in broken English, and there's complete silence in the room because nobody understood a word I was saying, except this guy who raised his hand. And I literally liquefied in place because I was, terrified of him. And he said something nice about my talk. He said, like, this is really cool, blah, blah, blah. Not asking a nasty question. So I re-solidified. And 2 years later, they offered me a job. So this guy's name was John Denker, and he was kind of the person I worked most with at Bell Labs. And the person next to him was Larry Jackal, who was the the department head who hired me. He was my boss. He ended up being my boss.
In closing, I want to ask you one last question that's a bit different, Yann, which is one thing I noticed about you is that you engage quite a bit in political discussions, when I look at Facebook, Twitter, and so forth. And it's kind of intriguing to me because I think a lot of us scientists, clearly not including you, but a lot of us kind of love science, partially because there is a way to determine the correct answer, and there's a way to determine this is now correct. We figured it out.
Right.
And in politics, everything's so, well, there are definitely clearly wrong things, but
yes,
it's much harder to identify the clearly one right thing that everybody in the world should agree. This is the way forward. I mean, that seems to never happen, right? So kind of wonder where that comes, where do you see that come from in your history, and also how important is it?
Very important. Okay, so the thing that gets me riled up in politics is not, necessarily ideology, classical political ideology, but it's more that, seeing people suffer for no reason, for reasons that are easily avoidable, and seeing that they suffer because there are decisions that are made that are completely irrational, or that are based on false information, or biased information, or false facts, or bad models of the world, and or self-interest also sometimes, but which is clearly the case in a lot of politicians. And so I'm my philosophy is that I'm an atheist, I'm a rationalist, and I'm a humanist. Okay, actually more than a humanist, because I think it's not just humans who deserve happiness, but also animals and everything. But I'm not a vegetarian, by the way. But because I'm a rationalist, as a scientist, we have to have at least one corner of our minds that is rational, it's completely rational. And when I see political decisions being made for example, reasons that are based on, religious myth from, sheep herders that, lived in the Middle East 3,000 years ago, that end up hurting people in really bad ways, I get riled up. I don't find that, that's completely against my humanism, right? I want to we were talking about objective functions, right? I want to sort of, maximize the long-term expected value of human welfare and minimize the long-term expected value of human suffering. And so, that's kind of a rational objective function. I mean, it's an objective function that you may agree or not with. And then what is the rational way of optimizing it? And it has to be based on your model of the world. Like, what is going to be the consequence of taking that decision on the long-term well-being of humanity?
Well, it seems if you had a really good AI system that could simulate the future, depending on decisions you make, you could actually build a tool that's very powerful to improve the whole human condition, how everybody's living.
That's right. So, I mean, this is, attempting to automate this completely would be like the ultimate technocratic, form of government, which I don't think I subscribe to. But I think there is something in this sort of model of intelligence, for an intelligent agent to act, whether it's a human or an animal or a machine, there has to be three main components, or four main components. One component is the objective that you want to optimize. All humans have this hardwired in our brain. There's something at the base of our brain called basal ganglia, and it basically computes how uncomfortable or comfortable we are. This is the thing that tells us you're hungry, you're hurt, someone is pinching you, you're burning, or whatever, right? The second component is what in our business we call a critic. So it's something that tries to predict, and that's in our prefrontal cortex. It's something that tries to predict in the future, am I going to be comfortable or uncomfortable? What is the future expected value of this objective that my brain computes for me? Then a third component is our model of the world. So it's something that predicts what is the world going to do, how is the world going to evolve in the future, And more importantly, how is it going to evolve if I take this action? So can I predict the effect on the world of the action I'm taking? Okay, so that's the model of the world. And then the last module, which you could call the actor, is the module that, given the objective and given the model of the world, tries to figure out the best sequence of actions that will optimize your objective given your model of the world. Okay, and robotic systems are based on this, right? You have all those components in
exactly.
In robots.
Yes. Mm-hmm.
Okay, so as a human, particularly a politician, but any human, any person, you can be evil or stupid in 3 different ways. First of all, your objective might be crooked. So your objective, instead of being the overall welfare of humanity, might be just your own self-interest. Okay, that means you are narcissistic, essentially. Okay, or sociopath or whatever. So think about your objective. The second component is your model of the world. If your model of the world is bad, then the prediction of what's going to happen as a consequence of your actions would be wrong, right? So you're going to say, stupid things like, we want to, forbid contraception because it encourages teenage sex. And that's factually wrong, right? I mean, there is a lot of studies that just show that it's just not true. If you, provide, free contraception to teenagers, you just reduce teenage pregnancy. I mean, it's just good, right? And a lot of countries have realized this. The US is kind of not quite yet. And it's because of religious reasons, irrational thought, right? It hurts people. And then the third way you can be stupid or evil is you have a good objective, you have a good model of the world, but somehow you cannot find a good sequence of actions that will optimize your objective given your model. And then you have some politicians that are stupid or evil in all 3 ways, right? They have a bad objective because they're narcissistic. The model of the world is completely wrong. And even then, they cannot actually take a sequence of action that will actually do the stuff they want to do, which to some extent make them less evil than if they were able to.
We're talking about humans
yes.
here, but AI could have the same issues, right? Has the same components, and each of these components need to correctly. Otherwise,
right.
we can't trust it.
There is this idea, this question of value alignment, right? Can you design the ultimate objective of the machine in such a way that it never kind of works against the welfare of humanity, right? And it might be, and people think maybe it's difficult to do this kind of design of this objective function. But then this is something that we are extremely familiar with as humanity. We do this absolutely all the time, designing objective functions to entice humans to do the right thing. We do this when we teach our children to behave properly. We teach them morals. We teach them, to distinguish, good from evil, to behave in society, to etc. Right? So we shape their objective function when we teach them all those things. We do this with laws. So laws are nothing more than shaping the objective function of humans and entities like corporations, so that whatever they do works for the common good. Okay, so this is not something new. This is not something that's new in AI. We've been doing this for thousands of years.
It seems you need something more than the laws. You need some notion that humans are above the law and can tell the AI when it's exploiting a loophole, and that is not actually what it's supposed to be doing.
That's
Maybe
right.
it's not above the law, but above the laws that it imposes on the AI. So something complex has to happen.
It's a little too early to be too riled up about those questions, given that we don't actually have the technology to build machines anywhere close to this yet. But yes, it's a problem that we are facing, that you're facing when you're building kind of, control systems and robots, and you have to design those objectives and do that. Yeah.
We face it all the time. You need to tell a robot what to do. You need to give it an objective in today's formalism, and including it needs to know when it doesn't know,
right?
And maybe defer to human operator, because otherwise it's just gonna be destructive in whatever it's doing.
We're back to this problem of representing uncertainty.
Yeah, that's definitely one of the big challenges.
Yeah.
Yann, thank you so much for joining us on the podcast. It's a real pleasure to have had you. Such a fun conversation, learned a lot. Thank you so much.
Well, thank you so much, Pieter, for having me. It was a real pleasure.